Okay, so part 2 is Pythagorean identities. Pythagorean. Probably already have a pretty good idea of what this is going to involve. It is derived from Pythagorean theorem. A squared plus b squared is c squared, right? But we're going to put it in the form of a trig identity, meaning something is true, always true. So we're going to the unit circle. Just going to explain it as I go. All right, so there's my unit circle on my x and my y axis. So if this is my y-axis, right, and this is the x-axis, okay, and I want to put my triangle inside the circle, it would look like that, right, a right triangle inside the circle. And I'm going to go ahead and write my Pythagorean theorem, a squared plus b squared equals c squared, just so we see it. That is for any right triangle. But this right triangle is on the unit circle. So what would be the length of the hypotenuse on the unit circle? Always. The hypotenuse of the triangle, yeah, it's the radius of the circle. And if we're on the unit circle, it's a unit, meaning 1. So 1. And which letter is that in Pythagorean theorem? C. C, right? So we already have that part. If we're turning Pythagorean theorem into trig, basically, you could say that, we'll call it 1 squared, right? Because 1 squared is just 1, right? So that's equals. So we're going to be simplifying this over here. Whatever. Good. And then the other two are the legs of the triangle. Okay. Well, this one is on the x-axis. And which trig function did we say goes with the x-axis? Back to this. So x-axis, which function went with the x-axis? Cosine, right? So that we could call this leg of the triangle cosine. And if we did, and that we'll say that's A, so we could write that as cosine squared theta. Let's put a theta in there because cosine always has to have a theta or an x or a beta or some letter, some variable with it. And we know the other leg of the triangle, the vertical one, the vertical component goes with y, and we know that y is sine. So we could call that sine squared theta. Okay, so I'll just get rid of the other equals 1. I don't need it. There we go. So we just wrote our Pythagorean identity, the original first version. So I'm going to write it real big over here. Cosine squared theta plus sine squared theta equals 1. And you'll see this all sorts of ways. Maybe there's a cosine squared on one side, and then on the other side it's 1 minus sine squared. Maybe all three of the terms are on the same side, and it's cosine squared plus sine squared minus 1 equals 0. You just have to be able to recognize that if you see a trig function squared plus or minus another trig function squared and a 1 in there, see if you can, if it's true, if you could rearrange it to match this, you have the Pythagorean identity. Now in this form, if that was -1, then it wouldn't really be the same now, would it? You'd have more things to do, but whatever. We'll talk about that later. But there's 3 versions of this I'm going to give you because we also talked about cotangent and cosecant and secant and all of these other things. So sometimes it's not cosine and sine. That's the original one. But if we took this, right, I'll do it over here. So cosine squared theta plus sine squared theta equals 1. what if we didn't have any sine squareds in it? What if we divide this whole thing by sine squared theta? Since that's 3 terms in the numerator divided by a single term in the denominator, we have to divide each one, and that will give us our second version. So if we have cosine squared divided by sine squared, cosine over sine, well, it's cotangent, right? Because sine over cosine was tangent. Cosine over sine is cotangent. And these are squared, so it would be cotangent squared. Plus sine squared over sine squared. Hello, what is that? Sine squared over sine squared. Yeah, it's just 1, right? When you cancel, you have to put a placeholder. Equals 1 over sine squared. 1 over sine is cosecant, and it's squared. So cosecant squared. So there's another version of the same identity that you might see. So this one gave us that version. And then there's a third version. Because here's when we divided by sine, we got rid of sine squareds. What if we did the same thing? We had the original one. But this time if we divide it by cosine squared, cosine squared over cosine squared is 1. Plus sine squared over cosine squared. Sine over cosine. That's tangent squared. Equals 1 over cosine is secant. So secant squared. So this version came from dividing out cosine squared. So those are the 3 forms of the Pythagorean identity that you will need to be familiar with and be able to recognize to be able to solve a problem. So now an example of a problem that you're going to be asked to do using a Pythagorean identity. If tangent theta equals -8 and sine theta is greater than 0, find sine theta and cosine theta. Okay, so if tangent theta equals -8 and sine theta is greater than 0, find sine theta and cosine theta. All right, so the way that I recommend doing this is I'm going to split it up into 3 parts. I'm going to start part 1. Part 1. For part 1, we're going to take these conditions. We're given some conditions. Right here in the problem. The first thing, those are conditions. And we're going to use those conditions to find out where this problem is taking place on our map. We need to make a map. Make a map. A quadrant map. To find out which quadrant this problem is taking place in. Okay, the first condition said tangent theta is -8. So tangent is negative. Is anything negative in quadrant 1? No, everything's positive in quadrant 1, so I know it's not in quadrant 1. Where else is tangent positive? Remember the little phrase I taught you was all students take classes? T says that everything is, the tangent is positive in quadrant 3 because sine and cosine are both negative, so negative over negative is positive. So it's not in quadrant 3 because our tangent is negative, and that would be positive there. So we've eliminated 2 of the quadrants. And then we're going to look at sine theta. Sine theta is greater than 0. Means that sine is positive. So the y values are positive. Y values are positive on the above the x-axis. So anything below the x-axis cannot be included. So we've figured out that our problem is taking place in quadrant 2. Okay, so the conditions, you're going to use those to determine the sign with a G, of the answer. Determine the sign, S-I-G-N, plus or minus, of the answer. Because as you work, if you're dealing with squares, Pythagorean, you're going to take square roots. If you take a square root, it could be positive or negative, and you'll have to figure out which one is your answer. So I like to do this part first. So then once I confuse myself with all of the rest of the math stuff that I'm going to be doing, I have this part done already. Because that's not that bad, right? Just figuring out where it's taking place. So now I know whenever I get my answer, it's going to be in quadrant 2. And so I can figure out if it's positive or negative based on it being in quadrant 2. All right, so then part 2. So that's my part 1. I'm going to come over here and do part 2. After you do that, then we're going to start working with identities. All right, so I'm trying to find sine and cosine. The only thing I really have is that tangent is -8. Because sine positive, that's not an exact value I can plug into an equation to work with. It's just, it helped me here, but it can't help me with an identity. So I need an identity with tangent in it. So if I did this one, tangent's in that one, I could write down the identity the way it is. 1 plus tangent squared theta equals secant squared theta. And then I know the value of tangent. So I can plug that in. 1 plus, instead of tangent squared, I'm going to do blank squared equals secant squared. Since I know that tangent's -8, I'll put a -8 right there. And then simplify it again. -8 times -8 is positive 64. So I have 1 plus 64 equals secant squared x, or theta. So 1 plus 64, that's 65. I can do that. All right, so can't simplify anymore, but if I could get rid of the squared, then secant, I could turn that into the reciprocal cosine. So let me get rid of the squared. You do it the same way you would get rid of a squared any other time. This one. Get rid of the squared by doing a square root. If you take a square root, it's plus or minus. So plus or minus square root 65 is equal to secant theta. And then the reciprocal of secant is cosine. So 1 over, or plus or minus 1 over square root 65 is equal to cosine theta. And that's what I'm trying to find is cosine theta, right? But I need to figure out, is it positive or is it negative? So cosine in quadrant 2, we'll go back to the map I made. Over here from the origin, I have to go to the left to go up. So cosine is negative in quadrant 2. So that means this is, because of my little map, I know this is negative 1 over square root 65 equals cosine theta. And it doesn't matter to me if you rationalize your denominators or not. So, up to you. Because if we're going to use this later on, we don't really want it rationalized because we're going to have to like unrationalize it. It's a big mess. All right, so this problem said to find sine and cosine. We did find cosine. So to find sine, we're going to do part 3. But the nice thing is we don't really need to use Pythagorean again because we already have cosine and we have tangent from the beginning. So if there was an identity that has tangent and cosine and sine in it, we could use that. Like the quotient identity that tangent theta equals sine theta over cosine theta. And I want it where sine is by itself because I'm solving for sine. So I'm going to multiply both sides by cosine theta. So sine theta equals cosine theta tangent theta. So sine theta equals something times something else. Cosine, I know, is negative 1 over square root 65. Tangent, I know from the beginning, is negative 8. So now I just need to multiply these two values together. They're both negative, so the negatives cancel, and it'll just be 8 over square root 65. So sine theta equals 8 over square root 65. Or if you want to rationalize it, you can. Just going to leave it. All right, so you have a worksheet that I printed for you. Have those 6 problems done by the time I see you Thursday, because we have the SATs tomorrow.